next presentation.
Okay, can everyone hear me okay?
Yeah, please.
Okay, great. So apologies, I haven't been able to make it to any of the previous talks because of the time delay to the UK. So it's 9 o'clock here in the UK, and I didn't fancy getting out of bed at 3 o'clock to start. Apologies to everybody. This talk is done jointly with my PhD student, Lloyd, at the University of Bristol, and it concerns the issue of trying to determine the attenuation of long waves through irregular floating ice. Okay, so this is a subject which has attracted quite a lot of attention over many years now, and this is our, let's say, modest attempt at trying to understand possible reasons for the attenuation of waves in ice. Okay, so this is the situation that I'm looking at or thinking about. So this is a representation of the marginal ice zones, some thin sea ice that is broken up into small segments. And as you can see from the picture, the composition of this ice is very, very complicated. So ice, I'm not an expert, I've not been in the field, but just from these pictures, ice looks complicated. It exists in many phases, so solid fragments of ice, there's pancake ice, frazzle ice, and grease ice. And even if you've got a single type of ice species, then you can see from the picture that you have varying different shapes and sizes. Okay, so trying to think of modeling of this is quite a difficult thing, I think. It's well known from physical observations that the wave energy, as it propagates through these vast areas from the open ocean towards the shore-fast sea ice, the wave energy attenuates. And as far as I'm aware, unless there's been recent developments or I'm completely unaware of the state of how things are, there's no yet consensus on what the physical mechanism is for this attenuation of sea ice. So I'll say this in just a second, perhaps. So it could be due to wave scattering effects. So the random nature of this broken ice creates some kind of multiple scattering effect, which causes the attenuation. Or indeed, it could be because of physical damping mechanisms. Okay, so in any physical system, there are natural losses. In the case of ice, it might be due to viscosity, it might be due to some loss of energy through bending or some other kind of physical mechanism such as turbulence. Okay, so this tries to summarize the quite complicated landscape of field observations into a single slide. And I just picked two graphs. There are many studies over which perhaps started in the early 1980s and continue to this day. The modern studies tend to be quite sophisticated and look at a number of different features. But in all of the studies, what you see is an underlying characteristic dependence of the attenuation rate on frequency. Okay, so the way that I described it here is that the height of the amplitude of the waves, and this perhaps means the wave envelope rather than individual waves. Okay, so there's two scales here. There's the individual waves traveling through the ice, and there's the rate at which they decay. So this is really representative of that envelope of wave amplitudes. And it decays on a spatial scale, which I represent here by Ki. And it turns out in these experiments that Ki appears to have a power law behavior on the frequency, the angular frequency. There's no reason why it should be a power law. But if you try and fit a power law relation to it, and this is what people do, it turns out that this power, beta, must lie somewhere or appears to lie somewhere between 2 and 4. This seems like quite a wide range, but this is kind of an exponential process. So 2 and 4, I guess, aren't quite so far apart. This is represented perhaps best in this diagram here, which shows instead a frequency an attenuation rate. This is on a log scale. This isn't on a log scale, so this isn't a straight line. But you can see that there's a dependence here. When the frequency gets higher, the attenuation gets higher. And if you try and fit one of these curves, omega squared or omega to the fourth, through this, you'll see that perhaps it lies somewhere in between those two powers. There's a similar attempt in this subplot over in the left-hand corner, of this plot here. So this is the dashed line, which is a power law fit. I think you probably can't see this, but this is period and something else, attenuation rate here. There's some experimental data which has been joined together with linear fits. And you can see that there's a broad agreement over a wide range of frequencies or periods, although there's some discrepancy for very low periods. Okay, so this is one aspect of, or one feature of the observations, which is that the attenuation rate appears to depend upon frequency. The attenuation rate also appears to depend upon other things as well, such as ice thickness, and also the coverage, the aerial coverage of the ice. So whether or not the ice is packed closely together or more dispersed. And I think these are harder things to try and work out experimentally, although there is some recent experimental evidence. The ice thickness is actually captured in this diagram here, and I'll come back to this later. So there's a series of blue dots and red dots in this diagram. And in this particular data set, they're distinguished by two different phases of ice. And the authors decided to choose the blue dots and put a straight line through it and ignore the red dots. But I'll come back to this later on. And then perhaps the most controversial thing about the whole issue of trying to find some way of parameterizing the dependence of attenuation on frequency is that when you try and fit this power law, you can see that it works over a wide range of frequencies, but for smaller frequencies, you tend to get a drop-off in the attenuation. And this is called a high frequency, low period rollover effect. And you have two camps of people who believe that this exists, and early experimental field data suggested that it does, and other people who think that it's just a feature of data processing and it's spurious and doesn't exist, and that this law, this power law, should exist over a wide range of periods. Okay, so the basic challenge that people have set, theoreticians and people working on sea ice have set themselves, is to try and develop a simple model of wave attenuation, which is supported by the data. Now, this is difficult. If you don't understand the reason for energy decay, okay, then you're going to come up with completely the wrong model. Okay, and as I said, there are two different ways of thinking about this. It might be that you've got some physical viscous damping, either in the fluid or within the ice itself, or it might be because you believe that localization, that is randomness and multiple scattering, causes attenuation. So I'm referring here to Anderson localization, which was originally sort of discovered in the 1950s to do with lattice systems in quantum mechanics. So we're going to set out and try and, so both my feet now are firmly in the second of these two. I'm going to look at the possibility that it's multiple scattering and randomness which creates this attenuation. So this is the model that we've looked at. The picture is accurate, apart from the fact that this is taken from a submitted paper, which is still under review. If you imagine for the time being that I'm not going to complicate things in this talk by talking about a variable bed. So in fact, the bed is flat. It's going to be at -h rather than h0. So I have a flat bed, and then I model the broken ice by chunks of conveniently, of course, this doesn't look like real ice, but this is my mathematical model, that I have rectangular chunks of blocks of ice which totally cover the free surface, and they're free from each other so that they can move independently, only in heave in the vertical direction. Okay, so these can bob, these are masses of ice which can bob up and down in the free surface. Okay, and this supports waves, and so I'm allowed to send in a wave in this experiment, this kind of mathematical experiment, I send in a wave from the left, not from an open ocean, but from a set thickness of broken sea ice. And then I enter a period, which is of length L, of random thickness of broken ice, and the randomness is this d of x function. And then after I have traveled a distance L, I return back to the thickness d naught that I had before. I say thickness, this is actually submergence, but thickness and submergence are the same to within rho I over rho W, 0.9, right? So they mean the same thing to me anyway. Okay, so I'm sending in waves, I enter a region of randomness, I transmit some energy and I reflect some energy. And I want to solve this problem. And I make some assumptions which help me in the modeling. Okay, so I want to make my model, given that, I mean, I've already made some assumptions here. I'm two-dimensional. I've got these rectangular blocks of ice, but I make some further assumptions to get a simple mathematical model. One is that the thickness of these blocks of ice, the width of each one of these, L, is a lot smaller than the wavelength. Okay, so that seems like a reasonable thing to assume. And the second thing is that I'm going to assume that I have shallow water. Now, this is the controversial thing. This helps me because it allows me to do some depth averaging. When I do depth averaging, I remove one coordinate, and I only have 2 dimensions, so I only get left with one coordinate in my system. I'm going to end up with a one-dimensional system describing wave propagation. So the depth is going to be small with respect to the wavelength. Okay, so this is my generic setup. And I'm going to suppress any of the mathematical derivation details here. I'm assuming linear shallow water theory. Okay, I homogenize the free surface condition by assuming, because I've got small chunks of ice, I can kind of smear things out and assume that it looks like in continuous media. Okay, it still has the same features, that the ice can move independently of one another. That's mathematical homogenization. And then I expand in a shallowness parameter, not just to first order, which is standard shallow water theory, but to second order. And I need to go to second order to pick up the acceleration of the ice. So this is a vertical acceleration. Vertical accelerations are removed in shallow water theory, but if you go to the next order, it's like a Boussinesque type approximation, and you pick up some acceleration. And when we do this and play around with the equations, we end up with a shallow water type equation. So it's an equation for the evolution of omega. I assume a single frequency little omega, confusingly. Now, omega is related to the wave height. It's my dependent variable. This is my frequency parameter, and then d of x contains all of the information about the varying thickness of ice. Okay, so it also includes the depth and the frequency, but this is what this function looks like. Okay, and significantly, I get extra terms because I've included the inertia of ice. So I get this gradient term and this weakly dispersive term here. Okay, so I've reduced the complication of ice down to a one-dimensional ordinary differential equation. So this makes my life very easy. And then you can argue whether or not I've just thrown away too much of the physics by doing this. Okay, but mathematically, we're now easy. We can send in a wave from the left, which we do by postulating that I have an incoming wave and a reflected wave. We have a transmitted wave to the right of the random region, and K naught here is implied by setting d of x equal to d naught. Okay, and then so I have a second order ODE, that generates 2 unknowns, and I can match my solution at the 2 endpoints, x equals 0 and x equals L, to determine what will be 4 unknowns, RL, TL, and the 2 unknowns that come from the ODE. So I can do this numerically. So what do I mean by, I haven't said anything about randomness now. I've actually got to choose what this d of x looks like. So this is how I choose my d of x. I choose it to be described as the base thickness d naught modulated by some randomness. R of x is a Gaussian random function with 0 mean and variance 1. Okay, and it's multiplied by sigma. So sigma tells me about the RMS, or the variance of the vertical variations. If sigma is 0, I have no randomness. If sigma is large, I have a lot of vertical randomness. Okay, and then the randomness is correlated by a Gaussian function. Okay, so lambda here gives me a scale, a horizontal scale of the horizontal correlations. So I have two statistical parameters describing the thickness or describing the randomness of the ice. I have sigma describing the vertical variations and lambda describing the horizontal variations. And in order to get information about attenuation, I sort of naturally have to choose L to be very, very large. I want to run this experiment over very long randomness sections of random ice because attenuation is very, very gradual. And so to pick up significant attenuation, I have to do this over a long time. How do I do this mathematically? So then I look, okay, so L needs to be very large. I look at the case where L is infinity. So I have a semi-infinite random section of ice. And now I can do some theory. I can do a multiple scales based approximation. I have a fast time scale, which is the length scale, the wavelength of waves propagating through the ice. And then I have a slow length scale, which is to do with the envelope. That's the attenuation, which is capital X. And the two are related by sigma squared. So this is a typical multiple scales assumption. I can expand my D function in terms of powers of sigma, because I'm assuming sigma is small. I can expand everything in terms of small sigma. I end up with a system of order sigma to the 0, order sigma to the 1, order sigma squared equations, which I solve in turn. And by the time I get to the order sigma squared equations, I get a solvability condition, which tells me something about the amplitude of the envelope of the waves. Okay, so there's quite a lot of mathematics goes into this, and in fact, there's a very, very subtle detail about how to remove decay, which is associated not with multiple wave scattering, but to do with phase cancellation when you do ensemble averaging. Okay, so there's a lot of stuff happens over this statement here. At the end of the day, you can show via this process that the wave field attenuates, okay, with an attenuation constant Ki. This is the thing that we're after. Okay, there's some reflection and some there's no transmission. Everything is reflected back. This is a conservative process. There's no physical damping. So if things are attenuated into the field, everything must be sent back. And the attenuation constant looks like this. There's a simple formula involving the statistics of the ice, the thickness of the ice, and the wave number in the ice as well. Okay, so this is the key formula. Okay, this is a prediction, a theoretical, simple prediction for the attenuation of ice based upon all of the assumptions that I've made. Okay, so what does this tell us? Well, for the shallow water assumptions that I've set out, K naught is proportional to omega. That's a shallow water dispersion relation. And so Ki does indeed go like omega squared, at least for small frequencies or long periods. So I get a power law relation which fits with the observations at one end, omega squared. It also tells me the attenuation goes like d naught squared, the thickness of the ice squared. It's not linear with the ice, but quadratic with the ice thickness. And the last thing that this tells me is that this isn't purely Ki goes like omega squared, but eventually for high enough frequencies, I get exponential decay. So the curve of x squared e to the minus x squared has a peak in it, and that peak is around this frequency here. So I get a rollover. I get a decay for high frequencies. Okay, and again, if you believe in high frequency rollover effect, this formula works for you. Okay, alongside that theory that I've just shown you, we do numerical simulations. So this is trying to determine numerically whether or not the attenuation rate that we see by making random ensemble averaging over a large number of random beds over long transects of ice actually matches this theory. Okay, so I pick some statistical parameters. I pick a long bed. I generate, say, 500 random beds. I solve my ODE numerically. I formulate a transfer matrix. okay, by assuming some general waves coming in from the left and from the right. And then I look at the eigenvalues of the transfer matrix, and the eigenvalues of the transfer matrix tell me about propagation, and they appear in reciprocal pairs. And I can extract the eigenvalues, and from the eigenvalues, I can extract the attenuation rate. So this alpha is different for every single random bed, but I then ensemble average over all of the alphas to create an average attenuation rate. Okay, so this is a simulation of a wave coming in from the left, going over the numerical simulation, going over random ice thickness. Okay, over this is the fluid bed. This is the random ice thickness, and I get some transmission and I get some reflection, but I also get some attenuation as I through multiple scattering as I pass over this random ice. Okay, and then here is two graphs showing the theoretical curve. Okay, this is the one produced for an semi-infinite random ice. That's the blue curve. So this is like frequency squared. Okay, this is where I've got exponential decay. This is approximately 1, where I get rollover. And then the dots are so the dots are scaled numerical constants from these from doing 500 simulations on ensemble averaging. Okay, so you can see that the numerical simulations compare favorably with the theory. The slight discrepancy is because I can't make my numerical simulations go on for L equals infinity. My L is large, maybe it's 1000, or 2000, but it's not infinite. These are for two different statistical beds, for two different statistical horizontal correlation lengths, just showing that it works for all parameters. And then quickly, the last thing I want to do is show how this model might apply to observed field data. So we've taken here some 4 panels of existing data showing attenuation. All of the bottom axes are periods or frequencies. All of the horizontal axes measure attenuation from different experimental campaigns. And we've just fixed one set of statistical parameters for all of the different plots here. Okay, so we haven't done parameter fitting for each plot. We've just fixed one point, which is that point there. And we've decided that this ice thickness corresponds to this point where we think that there is a rollover effect happening. So this is the peak attenuation, and this is the sweet spot where you get rollover. That's one point that's fitted. All of the other curves, 1, 2, 3, and 4, have been generated with the same statistics for different ice thicknesses, and then overlaid on these plots. So this is a comparison for shallow water, where the underlying attenuation rate is like omega squared. Okay, now we do something a little bit magical. We assume that if we were in deep water, the only thing that would change would be that K naught, instead of being proportional to omega, this is a horizontal length scale. So the argument is that shallow water is somehow, the depth of the water isn't affecting things. Okay, but if I just think about this as being dominated by horizontal length scales, then my K naught, my wave number in the horizontal direction, goes now like omega squared for deep water. And now my Ki would go like omega to the 4th, which is at the other end of the scale. And now I've done exactly the same thing. I've pinned one point statistically on this curve, generated all of the other curves for different thickness of ice. Okay, and now you see a better plot because this goes like omega to the 4th. And then the final thing that we've done is looked at the dependence on ice thickness. Remember, I said that for our model, this is quadratic rather than linear. We've gone back to the original plot that I showed you of Doble, where we put a straight line through some blue dots, and the blue dots was referred to ice in a compressive or rafting stage. And they ignored the red dots because they said that this data was due to ice in an expansive stage where you didn't get so much rafting and so much compression of ice. So this is ice, the blue dots is ice that's free to move vertically. And then my argument, these are two simulations with the same statistical parameters that we fitted to the previous curve, the shallow water and deep water. The underlying trend here is that it's quadratic, and the dependence here is just to do with the fact that we're using two different models. But hopefully you can see that there's some justification for thinking that this might be a good fit as well. Okay, so that's really all I want to say. We've used a very simple one-dimensional depth average model. Okay, we've thrown away loads and loads of physics, but we've shown that you have attenuation which fits in between the observed experimental or field observations. The model that we've come up with predicts a high frequency rollover effect. We've had to do some statistical parameter fitting because we don't know what sigma and lambda are, okay, but we've just done this once for each data set. So we haven't really tried to overfit parameters. I say that this model works, okay, so you might be thinking, well, this is great, everything's fixed, but there are so many approximations that we've made here, and there are so many things that we've not done, that it's difficult to say, even if this is still the right way of thinking about it, that is to say randomness is the cause of attenuation, it still might be that it's a physical damping mechanism, and this is just rubbish. And then we're currently considering extensions to finite depth, to looking at 3D, and to look at variable ice cover. So this is where you have some open water between the ice itself. Okay, so that's where the research is going. So with that, I've finished. Thank you very much.
Thank you very much, Richard. Now, please, we have 5 minutes for questions.
Okay,
Please.
you have mentioned that Ki wave number is proportional to frequency in shallow water approximation, but that is in case of free surface gravity wave. You have plate covered surface.
Yeah, I mean, I didn't write down the dispersion relation. I can go back. I didn't write down what it was for ice cover, but it is also exactly the same. It's proportional to omega, just like in the free surface open water case.
But in case of plate covered surface, it's K cube omega proportional to.
This is not an elastic plate. This is not an elastic plate with bending. It's a mass loaded. It's only got the mass loading term. It's not got the bending term.
Okay, thank you very much.
Another question, please.
I think Mike's got his hand up.
Mike.
Yeah, I have. Thank you, Dickie, for the talk. I hope you can hear me. I'm out and about.
Where are you?
It's a long story. I'm Wollongong. But,
it's always a long story, Mike.
I really enjoyed the talk, and and it's very impressive. I wonder. I guess for me, the thing that I wonder, one is, where does the group and phase velocity difference come into it? Like, I'm wondering if there's something there and the other one is, what would happen if you went to 3D? You know, if the localization effect becomes weaker, from my understanding.
Yeah, okay. So the first point you make about phase velocity and group velocity, I think it's a really important point. So we've done some work on the finite depth case. So obviously the phase velocity and the group velocity are the same for shallow water, right? It's just root GH for open water. Okay, so it's not frequency dependent. But when you get to finite depth, the phase velocity is the group velocity is half the phase velocity. And the phase velocity, now you have dispersion, right? And so both the phase and group velocity depend upon omega. And so I think the predictions that we make now for finite depth imply that it's not that the attenuation rate goes like omega to the 4th. It now looks like it goes like omega to the 8th, because you get an extra group velocity effect in the attenuation constant. So I think that is an important point that you raised. The
Yeah, so
other
I was
point,
kind of hoping that it would do the opposite and you come to omega to the 3. But anyway, yep.
no, it goes the other way. It goes the other way, I think, but we have to confirm that. Yeah, the localization in 3D, that's a tricky one, right? So it's not really 3D. Remember, right? It's really wave propagation in 2D.
2D, yep.
Yeah, so localization localization exists in 2D. It's not known whether it exists in genuinely in 3D. So I don't see too much of a problem, but obviously putting together a mathematical model would be a slightly different thing.
Thank you, Richard.
Thanks again, Dickie.
Cheers.
Time is ending. Only one small question from me. Did you account the interaction between ice spices model?
Oh, so yeah, I can see what you say, right? So here, I just assume that the two blocks of ice can move independently of one another. No friction, no interaction between the separate ice.
So this is clear mass loaded model, yes?
It's purely a mass loading model, yeah. So if you know about like Weitz and Keller, Peters, it's like a mass loading model like that.
Yeah, thank you. So time is over. We have next presentation.